For decades, space-based communication served a highly specific purpose. It was the transport method of last resort. If you were on an oil rig or a maritime vessel far beyond the reach of terrestrial fiber, you relied on a slow, analog relay system floating thousands of kilometers above the equator. That reputation was earned through severe technical limitations. Legacy satellite systems suffered from round-trip latencies routinely exceeding 120 milliseconds, alongside strict bandwidth caps that rendered them useless for modern enterprise networking. But the integration of 5G non-terrestrial network standards and free space optical communications has dismantled those limitations. This structural transition relies on dense low-Earth orbit megaconstellations rather than isolated satellites. By isolating a single data path through this new architecture, we see the resulting performance metrics. Latency drops to sub-30 milliseconds, enabling true Layer 2 carrier Ethernet capability directly from space. Physically, Orbit functions as a high-capacity, active routing fabric. The hardware floating above us now functions as a network of decentralized data centers operating in the sky. To understand how satellite networks are architected, you must begin with altitude. In space, altitude dictates the physical distance an electromagnetic wave must travel, which strictly governs signal propagation delay. Geostationary Earth orbit, or GEO, places satellites roughly 36,000 kilometers above the equator. This extreme height offers one massive benefit. A single satellite can provide persistent coverage over roughly a third of the planet. But this diagram illustrates the mathematical penalty of that altitude. To complete a single link, a signal must travel 35,786 kilometers up and the same distance back down, divided by the speed of light. That equation creates a hard physics limit of roughly 120 milliseconds of round-trip latency. A 120 millisecond floor breaks the strict timing requirements of 5G mobile backhaul and causes constant timeouts in modern enterprise wide-area networks. The alternative is low Earth orbit, or LEO, which drastically reduces the operational altitude to between 500 and 2,000 kilometers. Looking at this adjusted model, the difference is immediate. The propagation delay plummets, resulting in a highly competitive latency window of 25 to 60 milliseconds. But escaping the latency penalty introduces a severe velocity trade-off. To avoid falling back to Earth from this low altitude, a LEO satellite must travel at approximately 8 kilometers per second. Because it moves so fast relative to the ground, a single LEO satellite passes from horizon to horizon entirely out of view of a user in a matter of minutes. Therefore, achieving persistent, low-latency coverage requires abandoning the single satellite model entirely. Operators must deploy hundreds or even thousands of interconnected nodes, creating the megaconstellation. Every satellite network is structurally divided into 3 segments: the space segment, the user segment, and the ground segment. As you can see in this ground segment teleport, the terrestrial footprint required to track and connect to orbital assets is massive. Legacy systems operate on a Type 1 architecture, utilizing what is known as a transparent payload. This cross-section illustrates the core mechanism of a transparent payload, commonly called a bent pipe. The satellite receives an RF signal from a user, amplifies it, and bounces it directly down to a ground gateway, without reading or processing any of the data. This architecture contains a critical vulnerability. The satellite requires simultaneous line of sight to both the user terminal and the ground gateway to complete the circuit. If that satellite travels over a geographic void, like the middle of the Pacific Ocean, there are no ground gateways available to receive the signal. Without that terrestrial anchor, the satellite becomes useless as a routing node. A bent pipe architecture cannot scale into a truly global routing fabric because its operational capacity remains physically tethered to the geographic placement of Earth stations. To sever this tether to the ground, operators developed Type 2 architectures, which route data across orbit using inter-satellite links. Traditional radio frequency spectrum, like the L, C, Ku, and Ka bands, is too congested and too vulnerable to terrestrial jamming to handle the massive capacity these inter-satellite links require. The necessary medium to achieve secure, high-bandwidth connections between satellites is free space optical communication, lasers. This introduces an extreme mechanical challenge. You must connect and hold a microscopic laser beam between 2 nodes that are both moving at 28,000 kilometers per hour. The solution is a highly precise closed-loop alignment process known as PAT, pointing, acquisition, and tracking. During pointing, the initiating satellite calculates its target's predicted orbital position and mechanically orients its terminal. Next is acquisition. The satellite projects a wide optical beacon to sweep the area and search for its target. The target satellite's photodiode array detects this beacon and locks the connection by firing its own precise communication beam back at the initiator. But securing the lock is only the beginning. The ongoing tracking problem requires compensating for constant orbital drift and the high-frequency vibrations of the spacecraft itself, which threaten to break the optical link. The hardware solving this is the fast steering mirror. These highly polished surfaces are driven by digital controllers that measure pointing errors in real time. These micro-electromechanical systems make microradian adjustments thousands of times per second, absorbing the spacecraft's vibration to keep the laser perfectly still. By maintaining these locks, PAT mechanics fuse isolated satellites into a continuous, high-bandwidth space backbone, allowing data to be fractionated and relayed across the entire constellation. Forward momentum. The ultimate evolution of this orbital architecture is the Type 3 gatewayless optical mesh. Achieving a Type 3 network requires upgrading the core hardware of the satellite itself, moving from transparent analog transponders to fully regenerative payloads. A regenerative payload doesn't just bounce a signal, it actively performs digital demodulation, packet de-encapsulation, and executes Layer 2 or Layer 3 routing directly in the vacuum of space. Pushing this massive routing capability into orbit necessitates onboard software-defined networking to manage the flow of traffic autonomously. This topological node map models how that traffic is managed. Dynamic routing algorithms calculate next hop paths in real time, allowing data packets to intelligently bypass failed nodes or areas of orbital congestion. A data packet can now originate in New York, route through 4 different satellites in the optical mesh, and downlink directly to a terminal in London. Regenerative payloads turn satellites into autonomous routers, establishing an orbital infrastructure entirely independent of the terrestrial backbone. Standard terrestrial enterprise networks rely on physically fragile infrastructure. As seen in this exposed fiber optic line, terrestrial data travels through glass strands buried in the dirt, susceptible to backhoe cuts, natural disasters, and the vulnerabilities of daisy-chained microwave links. By combining regenerative routing with optical meshes, satellite operators are bypassing that physical fragility, delivering carrier Ethernet services strictly from orbit. This is the outernet concept, a satellite link that functions as an ultra-secure, low-latency local loop. Data stays in space from origin to destination, never once touching the public internet. However, treating low Earth orbit as a high-density networking switchboard introduces severe physical and environmental costs. Mega constellations are creating extreme orbital congestion. With thousands of nodes moving at 8 kilometers per second, close approaches between spacecraft now occur every 22 seconds. This density drastically elevates the risk of Kessler syndrome, a scenario where a single collision triggers a cascading chain reaction of debris, potentially rendering these orbital bands entirely unusable. Maintaining the long-term viability of this network requires new international regulatory frameworks, such as COSMOS, to enforce strict altitude limits, collision avoidance protocols, and manage aggregate spectral interference. The outernet demonstrates that global enterprise networking is actively being architected in the sky.